Session 4. My name is Peter Leonhardt, and I work for BT as the Technical Design Authority for the BT Global ABB network. I've had a long career in BT, but I suppose my most relevant period was working on the London 2012 Olympics, where I helped integrate the IBC International Broadcast Centre into the BT network, which is now the TV studio for BT Sport. This technical session brings together three excellent presentations. Firstly, by Andy Valdar, we have developments in telecoms network architecture. Secondly, we have Doug Williams, and he asked the question, does the exploding demand for data drive demand for gigabit connections? And thirdly, John Hart examines converged core network services, focusing on 5G network slicing and convergence, which are key technologies in next-generation networks. These presentations bring together and examine some of the key challenges and requirements and features of content distribution and content production, which have been discussed over the past 2 days here at the Congress. So it gives me great pleasure to introduce our first speaker, Andy Valdar. I'll just give Andy a brief introduction for those who don't know him, which isn't many. Andy Valdar has had a wide-ranging career in telecoms, covering network strategy, planning, standards, regulation, product management, as well as teaching and writing. After 30 years working for British Telecom, including 3 years on secondment to the United Nations in India, he joined University College London in 1999, directing part-time MSc programmes. Although now retired from UCL, he retains his visiting professor role and still lectures and supervises on a part-time basis. Andy has authored 4 textbooks on telecoms, is a director of the ITP board, chairman of the ITP Journals editorial board, and is currently president of FITCE Europe. He is a fellow of the IET and chartered engineer. Thank you, Andy.
Thank you very much, Peter, and good afternoon, everybody. My talk today is looking at things from a network architecture point of view, the key word being network. We've heard mention of architecture several times during the Congress already, which I'm delighted about. I'm going to make the case, I hope, that is actually the overall network architecture which determines whether particular technologies are successful or not within a network's an operator's network. So that's the challenge for me. So first of all, just a few words about what I mean by network architecture. Then I'm going to propose that there are 6 major developments that have or will make a big difference to the cost and quality of the networks. I give a brief set of examples and then bring out some conclusions. So, first of all, what is network architecture? Well, one way of looking at that is saying, what happens if you don't have a good architecture for your operation support systems? Basically, you're in this situation, and I've asked my students, what can we do to improve that? And some bright spark said, well, put some oil on the wheels, and then the chair can move faster. So clearly, architecture is about understanding what you need to do and how to organize things. It's a structural, functional approach to how things link together. And I think it's useful to recognize that there are actually a number of different views that you can take. There's first of all, number one is the commercial model, the relationship of the players and the roles that they take. And it's really about who's doing what to whom and who's paying for it. So it's those relationships that have to be decided before you actually get pen to paper and start designing the network. So that's the first view that I would recommend, the commercial architecture. And then there's the techno-regulatory view, which is where you would have an interface between one network and another, and that becomes the network interface. And then the relationship between the network and the user, the customer premises equipment, and above that, application interfaces. normally called techno-regulatory because there's usually some degree of regulation on those interfaces. And then there's one that we use a lot, which is an architectural view, which is basically logical or functional. And very often it's in a layer because engineers love layers. And a layered approach is, in terms of presenting the functions, usually very handy. And the final one is the one that everybody loves, which is this bit of equipment is joined to this bit of equipment. So it's the physical view. And really, it's those four views that, there's an example, by the way, of a physical view. And you can see that there's a large number of items there. The users on the left, the network, first network nodes is the first column, and so on as you work your way through. You'll be delighted to know, I'm not going to work my way through that diagram, it's merely to see what we mean by a physical architecture. So we have those four architectural views: commercial, techno-regulatory, logical, and physical. With that as background to what I'm going to be referring to, my personal choice of the top 6 architectural features are as follows. And all of these have or will add to the network functionality and the costs. And when I say functionality, I include management of quality as well. So the first one, which I think is really significant, is the shift of the user network interface. I'm going to explain all of these in a moment. So the first one is a shift of the user network interface, and the move to multi-service platforms is my second. My third is the layering, the separation of control from the transport functions. We've seen this referred to several times during the presentations at this Congress. The move to virtualization, convergence, and then finally programmability. So let's briefly look at what I mean by that and why they're important. The shift of the user network interface costs. Now, it's a truism that the major costs of voice switching are in the interface in terminating subscribers' lines. And I will move on from simple subscribers, don't worry. 70% of the total capital cost is in the line card that terminates a subscriber's line. 70% of the total capital cost of the switching. Therefore, if you could only move that cost out of the network into the hands of the user, then there would be a significant saving. So this is illustrated with this diagram here. At the top of the diagram there we have the simple subscriber's line, which is either copper or optical fiber coming into the exchange. And you can see that the black blob, which is the subscriber's line card, is the interface. It's either within the exchange concentrator or it's on the subscriber's premises, but at the terminating point, still technically within the network. Therefore, as the arrow at the top indicates, the operator's network costs still include it. However, when you move to the bottom of the diagram, we now have, for example, our IP phones or people speaking on Skype or whatever from a PC. And we can see that the interface cost is now actually in the subscriber's equipment. The subscribers are paying for that within their PC or their IP phone. So it's now moved out of the network operator's cost side. Now, why is that important? Think of the mobile situation. There is no per subscriber, per user terminating costs within the mobile network. That's all been moved into the handsets, which the user provides themselves, pays for. So the battery, the ringing, and the codec, all the things that you would normally have to provide within the network are now within the handset. Who pays for the handset? The user. So that's one of the reasons why, I'll come on to in a minute, the mobile network currently has the advantage over the fixed from a cost point of view. That was architectural feature number one. Number two was the multi-service platforms. And this is very common where there've been lots of individual platforms where we try and move all the services onto a single platform, a multi-service platform, MSP, as indicated from moving from A to B. Why is that important? Well, actually, you can get some capacity savings, because if you put lots of services over one platform, then by combining that, you add differences in time of non-coincident traffic peaks can be interleaved, and the total volume required when you support a number of services is less than a platform for each individual service. Forecasting errors. If you over-forecast capacity on one service, under-forecast on another, it swings and roundabouts when they're all on the same platform. And time to market. If you have a multi-service platform deployed already, the new service is immediately available nationwide or as far as the platform is deployed on day one. These are all significant savings in money, and capital savings due to the high volume platforms, operational savings because you're managing just one technology and not several. And these advantages, of course, apply to whatever technology, but nowadays they're being applied to moving everything onto an IP platform. So the only problem, because there's always some disadvantage, and there can be a problem in having a single IP platform, for example, where you're mixing real-time and non-real-time traffic. So you're managing different service categories, you're managing different quality of service requirements, and different tolerances to things like latency. It can be difficult in replicating all the features of all the services on the single platform. It has been likened to a Swiss Army knife. It does everything, but nothing very well. Nonetheless, overall, there is some advantage in moving everything onto a voice platform. The latest move in this direction, of course, is voice over IP. Now, the first thing that I want to make, and people always disagree with me, there is no inherent cost difference between packet switching and circuit switching of voice. People say, well, what about Skype? That's cheap, that's free, and there's nothing cheaper than free. But I'm talking about cost. They all use digital technology. They use PCM voice encoding. They use large-scale semiconductor technology. And you look inside an IP router, it looks just like looking inside a TDM switch. There is no inherent difference. However, and here's my first key point, if the architectural features of the shift of the user network interface and move to a multi-service platform, if those first two architectural features are followed, then IP switching of voice over IP, will be the cheaper. So there's point number one I wanted to make. Now, what that means for network operators who have a PSTN that they want to replace with IP is that it's only going to be viable to replace the PSTN if both those architectural advantages are deployed, which is one of the reasons why the wholesale replacement of the PSTNs around the world has been quite a lot delayed. So I think it's an architectural issue. The next one is the question of layering. So that's the separation of control and transport functions. I mentioned this as my example of how many different nodes and different technologies typical telcos have in terms of their platform variety. It has been likened to a bowl of spaghetti. A layering approach separates out the transport, the actual moving of the bits, and the routers and the access nodes from the control plane, and with some service provision above that. So that layered approach with appropriate interfaces is the architecture to move to, and that's been likened to a lasagna. So let's move from spaghetti to lasagna. The next one I mentioned was virtualization and network functions virtualization. NMFV, of course, has been an important feature that's been followed recently, and it's really recognizing that the functionality of a data network can be virtualized by abstracting the functions at the software level and using standard services, servers, storage, Ethernet switches, and so on. And you can use commercially off-the-shelf software, and that gives both potential capital and operational cost savings. Now, ETSI have defined a general architecture, and many telcos are already deploying it. And it's worth mentioning that it's usually associated also with software-defined networks, SDN. So here's the ETSI architectural model, and on the bottom left-hand side we have computing, storage, or network resources, so that's actually at the physical level there, which gets virtualized into virtual computing, virtual storage, or virtual networking. And the way that those components are pulled together is covered at the next level, where you have various network functions that you want to create on a pick and mix basis. And service is above that. To the right, we can see that we have the orchestration and various management layers. Software-defined networks I mentioned, which is essentially this idea of abstracting control into a control plane with API, application programming interface there, as the way of demarcating the two planes. And you can see that the software can control a number of resources in the data plane. And typically, time-critical actions, time-critical, stay in the data plane, and non-time typical can be managed more without such a time constraint within the control plane. Now that brings me on to network slicing, which we'll hear more about in a minute. Network slicing is a very important architectural feature in my view. What's happening is you have a number of resources, which when I say resources, I mean bandwidth occupying cables and routers, the way that you actually use capacity and features and allocate that on a virtual basis to a set of users or individual customers as appropriate. And by having these slices, slice 1, 2, and 3 are shown here, which can be permanently allocated to groups of services or groups of users or corporate customers. On a dynamic basis, we can change and reflect actual demand, and you can also allocate resources appropriately. You might even move towards guaranteed quality of service this way. So it's a very important function for managing quality of service for the individual services on a common service platform. So I think it's a very important architectural drive. Convergence, the word is used a lot, and we've heard about it already. My view on convergence is much more sort of prosaic. If we have two networks here, network 1, network 2, then there's a sort of service stack of access, core transport, switching and IP routing, control, and the service above that. You need to interwork, as shown there, at each of those layers between one service and another. However, if you can actually have a common core network and a common switching and so on, a common control, you've now moved into an integrated network approach. Still different services, service 1 and service 2, but the rest of the network is actually integrated. It's when you move to a converged service supported by this integrated network that you have the full capability. And a good example of a converged service, because we integrate networks and it's services that converge, the best example of converged service is fixed mobile convergence, FMC, where the common features are available and you can actually take your mobility through a cellular network or through the fixed network, and you get the same capabilities, would be a good example. Programmability is another key function in the architectural argument I'm making, where we can separate out the resources, as I say, and give access to change how those resources are used to both customers and service providers through an application programming interface. This could be important where major customers want to actually manage how their network resources on your network are being used in real time. So you can give that ability to not only the network operator, but to individual customers or for other service providers. So you can dynamically reroute and so on. So you can cope with instantaneous demands, breakdowns, as well as planned operational works. Right, so those are my 6 that I've chosen. There are a number of examples where these are already being deployed. I mentioned that the big advantage of moving the UNI has given the mobile networks a key head and shoulders move forward towards all IP working. Now my diagram here, one of my achievements in life is to put everything on one slide. And this is, so the 2G, 3G and 4G. When 5G comes along, I need a bigger slide. But the key thing is these are all side by side. They're all coexisting. And we've heard already in the description of 5G how the use of 4G, even though it may be enhanced a bit more, is still key to deploying mobile services in the future. And that's indicated here that at the moment, a lot of voice is still switched through the circuit switches. So as I've indicated with my smartphone down at the 4G level, you have circuit switch fallback for the voice as soon as you dial a PSTN number. Voice over IP or VoLTE over the 4G is shown on the bottom line there. Now the key thing about the 4G is it's moved to a single platform for all services and as an IP platform, as you all know. The other thing that's worth thinking about is if you look at the service stack associated with these nice simple diagrams there, this is the user plane service protocol stack within the LTE system, and we can see there are a lot of levels in that stack. And what does that mean in practice? Well, content is mapped into a frame, which is then mapped into a lower frame, and so forth. There's something about protocol stacks that could be addressed there. However, look at 5G, and we've already heard how 5G with the new radio system on the right is going to be supported initially with the core network of the 4G. And if you look at the 5G architecture which was presented, and this is just a quick example, we have the user plane, we have the control plane separated. So there's our layering that I mentioned earlier on. We also have, just referred to the top left-hand side, the network slice selection function is one example there. So that's already built now into the architecture of 5G. That brings me to a network vision. Is a vision or a hallucination, however you look at it. So we have the ability to bring that all together. So we have at the top of my left-hand side 4 and 5G mobile network access as appropriate, the fixed network down below, appropriate broadband access, and you'll notice that Wi-Fi is there, and people often forget that Wi-Fi is because it's a fixed service. You may be radio getting onto the Wi-Fi router, thereafter it's fixed. Going into a dynamic, converged, programmable network. Access to call centers still, data centers, and things like TV head ends would all be at that point. And on the right-hand side, the various packet and circuit switch networks. And above, there are our users or service providers coming in with APIs to get the programmability. So that could, bringing all those things together, an idealized vision for the network. So, to finish, I've identified 6 key major architectural developments, which I think have brought and will bring both functional and cost advantages to the networks, and it's that which is key driver. The shift of the UNI and the multi-service platform approach means that voice over IP replacement of the PSTN is viable. Layering and separation of control and transport functions makes virtualization possible, and that gives us the possibility to do network slicing, which gives us a good solution to managing quality of service on common platforms. Convergence can lead to new types of services, and the programmability gives customers, for example, direct control of their services. Thank you very much.